Okay, we are kind of adjusting. So if you have gone on and seen any of the 7.5 stuff that was on the website already, we actually are adjusting this a little bit to talk about just a little bit of logistic growth, but not getting super into a lot of this. And so just so you know, if you have, like I said, printed out any of those notes that were already on there. You don't have this on your note sheet, but most of the time we look at in mathematics before we get to this idea of logistics is exponential growth. And exponential growth is a lot of times where like they'll talk about things growing exponentially in the world, like bacteria in a petri dish. The spread of the flu in a school grows exponentially, right? But the reality of an exponential equation is it will look something like this. And exponential equations have a range that goes up to infinity. Well, the reality is I can't put infinity number of bacteria in a petri dish, right? I can't, there aren't going to be infinity number of people that get the flu once it enters a school, right? Because there's a finite number of people in a school. And so what actually happens is this idea of logistic growth models real world things that tend to start out growing exponentially, but the reality of real world is there's typically a maximum. Things do not grow to infinity, right? Usually there is some sort of maximum that it approaches. And so what happens is, this is what a logistic equation looks like. You guys have had a bit of an intro to logistics before. But what logistics does is the first part of it starts out looking like an exponential curve, like what I drew on the last page, right? But as it goes, what happens is eventually I start running out of room in the petri dish, or I start running out of people to catch the flu or whatever it is, and it starts leveling off at this some sort of maximum here. So it's approaching whatever the maximum is, number of people in the school, however much can fit in that petri dish, how many fish can fit in your fish tank, whatever it is. And what that's called is a carrying capacity. That maximum that it is approaching is what's known as a carrying capacity. And so it levels off as we approach that maximum. Our growth slows down, and eventually will level off at that maximum value. And that's our logistic model. Now, this is what a logistic equation looks like. Can you imagine right now taking the derivative of that and looking at its rate of growth, right? Its rate of change over time, and how it would be a positive rate of change here, and then we change, and that slows down, and we've got that little point of inflection where it's concave up to concave down, and that happens every time with our logistic curves, which is going to be an important point for us here in just a second. So if we look at the derivative of a logistic curve, which we look at quite a bit, so it says a logistic differential equation, meaning the derivative of that. Very important that you look at the relationship between these two formats of the same equation. What we are looking at is the derivative of a logistic curve. And there are some very important numbers to look at. Now, I prefer this one right here that is on the first one listed on the left, because I feel like it is easier to identify the typically important information from that equation. However, it could be handed to us in this format over here. It's a little cleaner inside here because there won't be a fraction, but and you can see your carrying capacity. So what are these numbers representing? P is representing the population, whatever that population happens to be in that situation. And that ends up being your variable that you will see inside the equation, okay? K is our growth rate, also known as your maximum growth rate. And sometimes that word maximum can throw people off, the maximum growth rate. And I think that's a lot easier to do when we have a 1 sitting here. And so a lot of times I will manipulate this differential equation to make it be a 1 here. We can always use our algebra skills to do that. And if I do have a 1 sitting here, this value in front of P will be our maximum growth rate. Okay. And then M is our carrying capacity, or the maximum, or what our population will approach over time. So as we get like farther and farther down our time, our x-axis, it's what our value will approach, and that is the maximum. And again, that's why I like this format when answering things like this, because it becomes the denominator of this as long as we've got a 1 here, becomes our denominator here. But if you have it in this format, it actually ends up being the first number here. It just makes it a little harder to see your growth rate there. Okay, so I'll usually move to that first option. Your logistic function, this is what you would have been introduced to back in pre-calc. You spend a little bit of time talking logistics, maybe, depending on where you're coming from. And so this equation is what you would have seen there. And again, some of the things that overlap between the logistic equation and the logistic differential equation that we just saw on the last page, you see that carrying capacity, that maximum, show up again. And this time it's the numerator of your logistic function. And you also see your maximum growth rate show up as your exponent here. Now notice it will be negative in our logistic function. It was not negative in our differential equation, but it's going to be negative here, and it would show up there. The only thing that becomes very important that you do need in your notes, because you do not have to have this memorized, but you have to be able to do this, is figure out this constant multiplier of E, this coefficient right here, which we would call A. So you're going to be handed a differential equation and asked to write the logistic function that would be the solution to that differential equation, right? It's antiderivative. And we should be able to pick out those two numbers from the differential equation, but what we can't get is A. And so this is the process that you would use to find that constant multiplier. You need to, first of all, figure out what the population is at time equals 0. P sub 0, or plug in 0 for your population. How much did we have at the start of that situation? Typically information handed to us, okay? A then becomes our maximum minus our population at time of 0 divided by the population at time of 0. Questions? Okay. The last thing that is typically discussed when talking logistics is, when is this function growing the fastest? Well, growing the fastest would be our growth rate. The fastest would be when that little tangent line is the steepest, right? That's when our rate of growth is the maximum value. And so if we were to follow our little tangent lines here, you can see that it's pretty slow growth here. Turns into that exponential type here, and my pen is almost vertical at this point, but then it starts leveling off again. So that maximum growth rate happens right here, and there are two very important things to understand about where that's happening. That is happening always at half of your maximum. So when will it grow the fastest? It will grow the fastest at half of the maximum, or half of the carrying capacity. Which also happens to be the point of inflection of your logistic curve. It's where it changes from being concave up to concave down. And that will be referred to in all of those different ways, okay? So understand all of those are all related to each other. Growing the fastest is half of our maximum, and that is the point of inflection of our graph. All happen at that same point. All right. So the best way to kind of get into this is just look at some examples here. So first example, it says the growth rate of a population P of bears in a newly established wildlife preserve is modeled by dp/dt equals 0.008 p times 100 minus P, where T is measured in years. So time in this particular example is in years. Now they're asking us about some questions here. What is the carrying capacity for the bears in this preserve? What is the bear population when the is growing the fastest? Now, what we would want to do is look at those two options we had and see which one we're looking at here. And this would be the option that says dp dt equals k over m times our population, m minus p, okay? From that, it's easy for me to identify our carrying capacity. Remember what that is in this picture. Our carrying capacity would be m, right? So the carrying capacity for this would be 100, or the maximum number of bears that can be in that preserve would be 100 bears. What is the bear population when the population is growing the fastest? Okay, well, when is it growing the fastest? Half of the maximum. And so there are a couple different questions that can be asked about this, but the question is, what is the bear population when it's growing the fastest? Well, the bear population is going to be half of the maximum when it's growing the fastest. If the maximum is 100, the bear population when it's growing the fastest would be 50 bears. Then the question is, what is the rate of change of the population when it's growing the fastest? Okay, well, the population is 50. The rate of change is your dp dt, right? Your derivative represents your rate of change. So they're asking us, what is the derivative's value when it's growing the fastest? Well, it's growing the fastest when the population is 50. When my population is 50, it's growing the fastest. So what we can do is plug in 50 to our derivative and see what our value is. So I'm evaluating our derivative at 50. Okay, and before I say anything, I want you guys to type that in your calculator and get an answer. Label your answer. Click on your label again. Okay, I think I saw the same answer on most pages here, 20, right? Some of it is the figuring out what did we just figure out. And remember that the kind of directions I've given us for figuring out a label go back to the like symbolic way of setting up your fraction for like your rate of change, dp dt. How do we label each of those individual things, right? It's population over time. So what we just found is the population, which is bears, per t is in years. So your label should have been bears per year. Any questions on that? Okay, let's do, I think I've got one more situation for us to kind of work through here. In an experiment involving the spread of disease, one infected mouse is placed in a group of 99 healthy mice. So let's interpret that, because we'll see several questions that are like similarly worded to this. If we've got one infected mouse put in with 99 healthy mice, how many mice do we have? 100 mice, right? Okay, I don't want that to be a surprise to us. The rate of change of the number of infected mice with respect to time, and this time our time is in days. follows a logistic model. If P is the number of infected mice and the maximum daily growth rate of the disease is 10%, write a differential equation that models the experiment. Okay, so they are asking us to write a differential equation. So go back to the two different types of equations we saw. When it asks for a differential equation, they're asking us for the one that says dp dt, right? That's the differential, that's the derivative version. To write our differential equation, I'll always write it with the one, the first version of it, but we need two pieces of information, right? If you look back at that equation, you need M, which is our carrying capacity or our maximum. And in this situation, what is that? 100, right? At the most, we could have 100 mice infected with this disease. The other thing we need to know is K, which is our growth rate, right? Our maximum growth rate. And this one is a little bit of a different format, but you may remember this. If they give us a rate as a percent, that we have to convert to decimal. So a lot of times we'll see it given to us as a percent growth rate. When we go to put it in our equation, we would convert. So our actual growth rate, move your decimal, divide by 100, move your decimal 2 spots, whatever, would be 0.1. So your K value refers to the decimal version of our growth rate. And then we just have to go put those in the correct places in our differential equation. So our differential equation, dp dt, will equal our growth rate. So I'm going to go with this version, kp1 minus p over m. Our growth rate is 0.1. P will always be the variable in this. Okay, it's our population. Times 1 minus P over our carrying capacity of 100. So first of all, understanding the question they're asking us, differential equation is the dp dt. Because the next one asks us to write the logistic function, and it kind of sounds like it's asking for the same thing, right? But the logistic function would be the antiderivative of this, where this came from. When they ask us for the logistic function, our answer should be P of T equals at the end. Okay. Now, in order to go from the differential to the logistic function, we need to know two things. The first thing we need to know is what the population was at time equals 0. Now, our population is referring to the number, look up here, population is the number of infected mice. So at time equals 0, what's our population? 1. We had 1 infected mouse, English, at time equals 0. Okay, so we need to know P of 0. The second thing we need to then figure out is A, okay, to write our logistic equation, because everything else we already have gathered that information. But I now need to find A, and A is going to be our carrying capacity minus P sub 0 divided by P sub 0, which in this case is, probably don't even need a calculator. 100 minus 1 is 99, divided by 1 is still 99. And now we go back to that equation that I gave us at the beginning for our logistic function. And our logistic function should be just a normal equation, P of T, population with respect to time. It is our maximum or our carrying capacity over 1 plus, it's always 1 plus. And then what follows that is going to be the A value that we just calculated, 99. Don't forget the E, raised to the negative growth rate, 0.1, T. There's your variable, time. Questions? All right. Now for a little bit of algebra. Okay. Same experiment involving the spread of disease. We've got those 100 mice. It says find the time it takes for half of the population to become infected. This is a very common question in talking about logistic, is they'll ask you, when will it be this amount? When will it be this amount? When will it be half of the maximum, okay, or half of the population? Well, that is our logistic function, and we'll be solving for time, right? The question is when, so we'll be solving for time. So if we look back at our logistic function, we want it to equal half the population. Our population is 100, so we want to know when will it equal 50. So I set it equal to 50. And this is where, again, a little bit of algebra here. You, again, may or may not have seen this back in pre-calc, but there's my variable that I'm trying to solve for, currently in the exponent of my denominator, okay? So a couple things I would do is I would first of all start by multiplying both sides by 1 plus 99e raised to the negative 1t to get that out of my denominator. But then also I want to get rid of the 50, so I would divide by 50, and it's going to kind of look like those two. Well, actually, let me just do this step by step here. We'll one time here show all the steps. If you understand that this is going to solve the same way every time, you'll be able to speed this up, but that allows me to get that out of my denominator. That's the first thing we always need to do, is get our variable out of the denominator so we can access the variable. And ultimately, I want it by itself. So I'm going to divide now by 50. To solve an exponential, I have to have that exponential term all by itself. So now I have to use my algebra skills so that I have now solved for e raised to the 1 minus negative 0.1t. So there are two steps that I need to do to get that accomplished. Subtract 1. Divide by 99. And now I can flip to logarithmic, right? Log base e of 1 over 99, natural log of 1 over 99, equals my exponent. This is why I told you you needed a calculator, because now I need to consult my calculator and figure out what the natural log of 1 over 99 is. And last step, divide by negative 0.1. And tell me what the answer is. Did you say 951? Time, oh, I didn't mean to cross that out. Time is in days. Okay, now that was a lot of steps, but please understand that every single logistic function is set up the same. And as you guys look at my work, as you're working through your worksheet, when we're doing a similar problem like this, you will see me set this up and then jump basically to here or here, because it's going to be the same thing every time. Okay, these two are going to look like they flip. Simplify that. You'll always then subtract 1 and divide by a, always, okay, to get you to this fraction, which then we'll take the natural log of and divide by the number in front. I don't need to see that work. Set up, do the work to get you your answer. You can show as much or a little as that as you need to. Questions? Okay. One more thing to talk about here, same situation. First of all, understanding the question and understanding the needed information. Okay, so we've got that same set of 100 mice. And the next question they're asking us is they say, okay, well, what if we changed the initial population to 5? And then look at this next question. What is the limit of P of t as x approaches infinity? Oops, and that should probably say t approaches infinity. As t approaches infinity. What is that asking? What is it asking when it says what's the limit of P of t when t approaches infinity? It's asking for your carrying capacity, isn't it? It's asking for what is the population going to approach or head towards as time goes on, right? Well, as time goes on, we're going to get really close to our carrying capacity. So back up. Why did they change the initial population? Does it impact your answer at all? How many mice can get infected in the long run? Does it change by how many were infected at the beginning? Not at all. So completely unnecessary information to distract us purely. This is asking you for your carrying capacity. Right? That's what that question's asking you for. This has no impact. Right? However many we started with does not change the maximum. So our answer is still 100, regardless of what we started with. So maybe we started with 10 mice infected. Great. We can still only have 100 infected at the end. We might just get there faster. Yes. No, probably good habit. Are you saying I should label my answer? All right, so then the next question, again, kind of interpreting what it's asking us for. So again, they change our initial number of mice infected, right? So they're saying, okay, well, now population at 0 is 2. When is the disease spreading the fastest? Still at half of the carrying capacity, right? So again, changing that to understanding the question, still should be 50 mice, okay? And actually there's a bit of a typo on this one. It shouldn't say when is the disease. It should say what is the value, actually at what value? At what value of P is the disease spreading the fastest. Just so you can kind of recognize the wording again as you see those questions later. Our population would be 50, okay, mice. And again, this still has no impact on that, right? Because spreading the fastest, again, still is just half the max or half the carrying capacity. All right. Questions? You guys have a worksheet today. You have learned everything for chapter 7. So at this point, it is review. Preparing for your test. We will review tomorrow, Friday, Monday. You will test on Tuesday.